Alright, so I called this section 14A2 since it's not in your book. It's stuff that we could look at between section A and section B. So we looked through the homework and we said the limit of a polynomial, and make sure your exponents are greater than 0. But the limit of a polynomial is simply f of c. As x approaches c, the limit's f of c. Plug it in, evaluate. Okay? We also saw that the limit of a constant is the constant. Alright, so if our function just equals some number b, then the limit will always equal b. Another thing we didn't necessarily look at from the homework, but is kind of a simple concept, and that is that the limit of a constant multiple of a function is the number times the limit of the function. Alright, so take a look at this here. We have the limit of some number b times a function f of x. That's going to equal b times the function. And really, where this is particularly helpful is in keeping your numbers a little smaller. You know, for example, let's say you had something like this. The limit as x approaches 5 of, let's say you had a 12x squared plus 24x minus 36. Okay? Well, your numbers might get a little bit bigger than you care to deal with. So what I could do is recognize this instead as the limit as x approaches 5 of 12 times, so I see I have a common factor, 12 times x squared minus 2x minus 3. So I can see this as a multiple of this function x squared minus 2x minus 3. And the reason why that's helpful is because, yes, I could have just plugged in 5 right off the bat, but if I see this, what I could do is actually wait on that 12, do 12 times the limit as x approaches 5 of just x squared minus 2x minus 3. I plug a 5 in there and I get 25 minus 10 minus 3, which is 12, and that's just 12 times 12, which we know is 144. Okay?
B times f of c.
Yes. Yeah. And in this case, it's b times f of c. You can actually do this with any function you want. It doesn't have to be a polynomial. But yeah, in this case, since it's a polynomial, it's b times f of c.
Can you go back up for a bit?
Sure. Okay. So those are 3 basic limit theorems. I want to look at 4 others as well. And again, like I said, this isn't necessarily something that you'll be tested over specifically, but it is something that as you do different limits, these can make finding those limits a whole lot easier. Okay? There's a lot of different ways to find limits, whether you're analyzing the graph or you're using some of these limit theorems, but these often will make things a little bit easier. Okay. So let's take a look at another one. The limit of a sum. Okay. The limit of a sum. And actually, I'm going to modify this. Oh, I locked it. Okay. Let's say I was doing this. that's a little better example to show how this can be useful. You see here that this function x squared plus 3x plus radical x over radical x minus 1, we can evaluate, or we could have evaluated, except right here the denominator is going to end up being 0. Okay, so what we can do with this limit theorem here, the limit of a sum equals the sum of the limits. So what I can do is I could break this down into two separate functions. I see that that's a polynomial, so I'm going to write that limit as x approaches 1 of x squared plus 3x. So I can just evaluate that part, and then I'll look over here at the limit as x approaches 1 of root x over root x minus 1. Okay? So here I plug it in, 1 plus 3 is just 4. And then this I'll have to figure out another way. Okay? As x is approaching 1, and remember we could use our graph to figure that out. But we know that there's some sort of an asymptote at 1, and we need to look at what happens as we approach 1. So you can make yourself a little table. And look at values on either side of 1. So you could look at, let's say, 1/4, 1/2, and 3/4. And then on the other side, you could look at 5/4, 3/2, and 7/4. 1 and 3/4. And you could evaluate that function for each of those. Okay, if I have 1/4, it's going to be 1/2 over 1/2 minus 1. So that's 1/2 over negative 1/2, that's a negative 1. Okay, if I have a half, that's root 2 over 2 over root 2 over 2 minus 1. You figure that out, it's about 0.707 over 0.707 minus 1, so that'd be a negative 0.293. Okay, obviously you can use your calculator for that, but that would be about let's see, that'd be negative what? 2 point something. Okay. Then if you did 3/4, again, you can use your calculator for this, but you'd have root 3 over 2 over root 3 over 2 minus 1. You divide that, and you're going to get something even bigger than negative 2. Okay? So you'll see that this is going down as we approach from the left side of negative 1. Okay, I'm not sure exactly what the values would be, but you see that it's going down. Then you come over here to 5/4, and you have a root 5 over 2, root 5 over 2 minus 1. Okay? And that actually equals 1.1 over 0.1 approximately. So that would be 11. Okay. And you could keep going again. But what you'll see is that this will actually start getting smaller. Alright, so what you saw happen was this function actually has a horizontal asymptote at y equals 1. That's what it's going to look like. So what would the limit here be as x approaches 1?
Not exist.
Yeah, you could think of it that limit doesn't exist. If I did all my calculations right. So, yes?
I'm sorry, can you explain how you chose those x values to plug in?
Because we want it as it approaches 1, I went on either side.
Okay.
I just went by quarters. And that's where you can use your calculator with the table. So. Okay. So, in this case, what's 4 plus does not exist? It doesn't exist.
Like an imaginary number for answer.
Alright? So, this limit of the entire thing does not exist as x approaches 1. Okay? If we had our original function, or our original limit as x approached 3, I think I had it at, in that case you could have just evaluated all of it, but you could have taken the limit of each part separately, found out what that is, and then add them all together. Okay? But you'll notice as we're looking at the part that we're not sure about, this part we could disregard for the moment because we already knew whatever this is, we'd add it to 4. Okay? So, the limit of a sum is the sum of the limits. That actually directly translates over into one of our derivative theorems, which is the derivative of a sum equals the sum of the derivatives. Okay? Another one here, the limit of a product is the product of the limits. Well, this one doesn't translate directly to derivatives. There actually is a product rule. But here, if we're finding the limit as x approaches 5 of x squared plus 2 times x minus 7, we don't have to FOIL. We can simply take the limit as x approaches 5 of x squared plus 2 times the limit as x approaches 5 of x minus 7. Alright, so here we have 25 plus 2 is 27 times 5 times negative, or 5 minus 7 is a negative 2. So we just do 27 times the negative 2, or negative 54.
So this one, if we didn't know this rule, would it come out differently?
No, if you FOILed and then saw that as a polynomial, and then just plugged it in, it would work as well. But you'd have to do the FOILing, or, I mean, you might recognize that as a polynomial as it's written.
It's like if we do order of operations and we have an x, we can just go. Okay.
Yep.
So this is just to make it easier.
Yeah, keeps your numbers smaller. And there will be functions where particularly something like this would be helpful. Yeah, I'm keeping our functions that we're taking limits of relatively simple, but they're not always going to be polynomials. Yeah, for example, like this one. I'd say, well, that's division. Yeah, But what if I rewrote this? Okay? What if I rewrote this as the limit as x approaches 5 of x squared plus 2 times the square root of x plus 3 to the negative 1. Okay? I can then take the limit as x approaches 5 of the x squared plus 2, which is just a polynomial, and then I can multiply that by the limit as x approaches 5 of the square root of x plus 3 to the negative 1. Which I could also write as x plus 3 to the negative 1/2, but either way. Okay, so now I can look at just my polynomial function, which I know is continuous everywhere, so that's 27. And then I can look at my radical function. I've got 1 over square root of x plus 3. And I can figure out what that is and think about the asymptotes and all that sort of thing to see, is this continuous around x equals 5? Yeah, this is not continuous anywhere less than negative 3. Okay, so x has to be greater than negative 3, because we can't have a 0 in the denominator, and we can't have a negative in our radical. So as long as I'm approaching an x greater than negative 3, I can just plug in to find my limit. So 5 plus 3 is 8, the square root of 8, I have 1 over the square root of 8. Okay? And you can rationalize that. Okay? That'd be 2 radical 2, so we'd have 27 radical 2 over 4 once we simplified the whole thing. Okay. Any questions so far? Okay. A couple more here. I'm going to see how you guys can do with some of these. The limit of a power, and by that I mean a function that's raised to a power, is just the limit of the function raised to that same power. Okay? So you'll see here I have some function raised to a power n, and I'm saying that that's going to equal the limit of the function itself, and then that limit raised to the n power. Okay? So here we have this function x squared minus 21 raised to the third power. I can, instead of doing it as written, I can do the limit as x approaches 5 of x squared minus 21 and raise that to the third power. Okay? So what's the...
What is the last one?
Oh, we got one more. So what's the limit before we cube it?
16. No, 4.
4. 5 squared would be 25, because here again we're just taking the limit of a polynomial. So 25 minus 21 is 4. Then we can cube it. Okay, 4 cubed is what? You guys know that one? 64. Okay. So actually, let's think back here for a second. Here we had this limit as x approaches 5 of x plus 3 to the negative 1. Instead of the square root, that's a 1/2 power, right? So that's, if it were to the negative 1 as well, it would be the negative 1/2 power. Okay? So if I want to find that limit, I can find the limit as x approaches 5 of just the x plus 3. And then raise that to the negative 1/2 power. Okay? So you'll see, here's something that's not a polynomial, but by using the power rule, we can focus on what is a polynomial and then apply this rule to it. So the limit here was 8, so now I just have 8 to the negative 1/2 power. Okay? So again, that's something, the better you know all these different rules, the easier some of these more complex functions are to find limits for.
So that's 1 over root 8,
Yeah, it'd be 1 over root 8.
or 8. Root 8 over.
Which is, you know, and that's 2 radical 2. So that would be root 2,
Wait, why is there construction? I thought we were done.
root 2 over 4. Okay.
That makes the colors.
Banging on something. Now it's
We're
now
fixing
it's
the
going to be
iPad
the
downstairs.
experiments downstairs.
The iPad lasted like a day.
All right. So any questions about our limit of a power? Okay. Last one here. The limit of a rational function is the quotient of the limits, and this one is true as long as the limit of the denominator does not equal 0. Okay, so see what you can do with the first one. The limit as x approaches 3 of x squared plus 2x minus 5 over x plus 2. Okay, so what do we get for the numerator? 10. Okay, 9 plus 6 minus 5 is 10. How about our denominator?
5.
It's 5. So our limit's 2. Okay? You might say, well, we did something like this on Friday. And that's true. If you remember, the general rule I gave you on Friday is you're allowed to just evaluate as long as we are continuous around the value of x that we're approaching. Okay? Well, now we're actually looking at some theorems that kind of show us why that's the case. Alright? The fact that the denominator does not equal 0 shows us that we're continuous about that value of 3. Therefore, we could have just evaluated from the beginning. Okay? Now, there will be cases like this one where that doesn't necessarily work. Okay? Here, if you plugged in 36 into the denominator, you're going to get 0. Okay, so what you can do, however, is look for an opportunity to reduce. Okay, and remember we said if you can reduce, then it's not an asymptote, it's a point discontinuity, right? So really what we're trying to figure out here is x equals 36 an asymptote? Or is it a point discontinuity? Because if it's a point discontinuity, then we can just reduce and then evaluate, and we'll get the right value we're looking for. Okay? So, what I would have to do with this one is I would actually have to take and factor my numerator. I'd say, well, that doesn't factor. And I would say, it's not real obvious, but yes, it actually does. And this is something we do in math a lot. And as you get more comfortable with math, the more you'll do things like this, where I see something I want to happen, so I just make the other part look the way it needs to get done what I want to get done. Okay? I want to cancel this out, this radical x minus 6. If I can't somehow get a radical x minus 6 in the numerator, then I can't cancel it. That must have been an asymptote, and I'm done, okay? But there actually is a way, and it's to see this as the difference of squares, okay? Now, when you guys had Algebra 1 and you were learning how to factor polynomials, you probably learned a pattern called the difference of two perfect squares. You guys remember doing that? You should. Okay. And you saw, oh, well, if I have x squared minus 9, you know, that's a perfect square and that's a perfect square, so it factors into conjugates, x plus 3 times x minus 3. And you came up with those conjugates by taking the square root of each of the terms. Square root of x squared is x, so I put an x there and there. The square root of 9 is 3, so I put a 3 there and there. Okay? What they don't tell you in Algebra 1 is that they don't have to be perfect squares. Okay? This is the square of something. Okay? X is simply the square root of x squared. Right? Minus 6 squared. So that would factor into the square root of x minus 6 times the square root of x plus 6. And look, I can cancel those out now. Alright? So that's kind of a advanced connection to our Algebra 1. but it's kind of a neat tool to use, and it comes in handy sometimes. So the square root of 36 is 6 plus 6 is 12. Now we can just evaluate. That 36 was just a point discontinuity. Okay? Does that all make sense?
So if you can't reduce, then it's asymptote.
Yeah, if you can't reduce, it's an asymptote. So what I found out here actually is that this graph, here's our parent function radical x. It's shifted to the left 6 spaces. Okay, so our graph actually looks like this. However, there's a point discontinuity down here at the value 36. Okay. So that's what that graph would actually look like. Alright, so what if none of these rules apply? Well, then just use a table or use the graph itself and take a look at it. Okay? But I thought that would be helpful in the long run. This is beyond what the IB expects you to know about limits, but the IB isn't the end of your life, so you guys will see a lot of this stuff and more advanced when you get into calculus in college, which probably the majority of you will end up taking. So, alright, or juniors, what are you taking, AP Calc next year? No? Don't know?
No, I have no idea.
Don't know? So, but either way, it'll be helpful in the future for you. So, alright, so that's as far as I wanted to go with the limit theorems, specific limit theorems. We want to hone in, however, on limits at infinity. Okay, and this is really where we're starting to make the transition into calculus, because a lot of what we're doing is finding the limit as something approaches infinity in order to come up with, say, an integral. Or we're finding the limit as x approaches 0 as well. There's kind of those two values, whether we're approaching infinity or approaching 0, those are both helpful. So I'm going to separate this here.